This video will cover the equilibria of weak bases. Our focus will be on calculating the pH of a weak base solution, but we'll also learn how to determine percent ionization. Everything we have learned about using mice tables with the assumption and possibly the quadratic equation directly applies here. In particular, the strategy for weak bases is nearly identical to that of weak acids, which is shown in another video. There's one extra step when dealing with weak bases, and we'll talk about that in a little bit. The stoichiometry of base ionization is always 1-to-1, so our exponents are 1, and our change rho will always be minus x or plus x. The mass action expression is written to exclude liquid water, and the equilibrium constant has the symbol Kb, which refers to the base ionization constant. The other type of calculation we'll see here is percent ionization, which equals the molarity of hydroxide divided by the molarity of the initial weak base that we're writing as A minus times 100. This is the same setup as X divided by the initial A minus times 100. The calculation for percent ionization is mathematically the same as our assumption check. The general strategy to calculate the molarity of hydroxide at equilibrium is the same as what we've used previously. Set up the mice table, write the mass action expression, solve for x using the assumption, check the assumption, and use the quadratic equation if the assumption fails. After solving for x, which equals OH minus, we'll calculate POH equals negative log of OH. This step is often incorrectly assumed to be pH equals negative log of H plus. So be deliberate in recognizing what X means. X equals OH minus for weak base equilibria. Once you have POH, then rearrange the equation pH plus POH equals 14.00 to solve for pH. In our first example, we are asked to calculate the pH of a solution of pyridine, which is a weak base. We know it's a weak base because we have a Kb value that is given to us. So the first thing we do is write our equilibrium for weak base. I usually include the water for these only because it reminds me of where my oxygen comes from that ends up in the OH minus. So H2O plus A minus, which is my generic term for my weak base, goes to HA plus hydroxide. This is a mice table, so our units are molarity. And we're just going to basically cross out the water because it doesn't get incorporated into the mass action expression since it's a pure liquid, and so we're just not even going to do anything with it. So filling in the values for our ice table, we have 0.533 for the weak base, 0 and 0 for the HA and OH minus. The change rho is minus x plus x plus x. And so we have 0.533 minus x, x, and x. We will never see a perfect square for these weak base problems, and so we will always set out to use the assumption. We will ignore the change in x, and then we'll check our assumption later. So writing our mass action expression just with the symbols, I still think that's a good idea, even though our stoichiometry is 1-to-1. We have HA times OH minus divided by A minus. So we'll plug in what we have. We have Kb, which is 2.0 times 10 to the negative 9, equals x times x, or x squared, divided by 0.533. Cross multiplying and solving for x, we have 2.0 times 10 to the negative 9 times 0.533 equals x squared. And we take the square root of both sides, and that will give us x. For the sig figs, we have two and 3. So our final answer will be rounded to 2. Doing the math, we have 2.0 times 10 to the negative 9 times 0.533. Take the square root of that. Rounded to 2 sig figs gives us 3.3 times 10 to the negative 5. We still have some work to do. We need to check the assumption, and then we need to use x to finish the problem. But I think it's worth writing down at this point that x is equal to the hydroxide ion concentration. As I mentioned earlier, the most common mistake with weak base equilibria, with these types of problems, is forgetting that x is hydroxide and not H+. Checking our assumption, we have 3.3 times 10 to the negative 5 divided by 0.533 times 100. This will be rounded to 2 sig figs. So we have 3.3 times 10 to the negative 5 divided by 0.533 times 100 gives us 0.0062%. So that is definitely okay. So we have 2 more calculations. The first is to calculate POH, which is negative log of the OH. So negative log of 3.3 times 10 to the negative 5. We have 2 sig figs, which will end up as 2 decimal places in our final result. So taking the negative log of 3.3 times 10 to the negative 5 to 2 decimal places gives us 4.48. We're not done yet. This is a weak base, so we need to do that final step, which is pH equals 14.00 minus 4.48. Everything here is 2 decimal places, and so our final result will also be 2 decimal places. So 14 minus 4.48 gives us 9.52. This was a solution of a weak base, and so a pH greater than 7 makes sense. In our next problem, we're given a weak base again, and we're asked to calculate the pH and percent ionization. We'll start by writing our equilibrium. So we have water plus A minus goes to HA plus OH minus. So we have our mice table. Strike out the water and fill in the rest of the table. So for A minus, we have 0.322, and then 0 and 0, minus x, plus x, plus x. Our E row is 0.322 minus x, x, and x. Our mass action expression is HA times OH minus divided by A minus. So we'll plug in the values, and we have 5.9 times 10 to the negative 4 equals x times x, or x squared, divided by 0.322. And as is typical for these problems, we did ignore the change in x, but we're going to check it after we solve the problem. So rearranging that now, to solve for x, we have 5.9 times 10 to the negative 4 times 0.322 equals x squared. Take the square root of both sides and check our sig figs. We have 2 and 3, so our final result will have 2. And doing the math, we have 5.9 times 10 to the negative 4 times 0.322. Taking the square root and rounding to 2 sig figs gives us 0.014. And again, this is equal to hydroxide. We're going to check our assumption. We have 0.014 divided by 0.322 times 100, and we get 4.3 So our assumption is okay, and this calculation is also equal to our percent ionization. So our percent ionization is 4.3%. To calculate the pH, we first need to calculate the pOH. pOH is negative log of the OH, so it's negative log of 0.014. 2 sig figs becomes 2 decimal places. I know we see this a lot, where it's 2 sig figs becomes 2 decimal places. It's not always the case, so it is important to check. Taking the negative log of 0.014 gives us 1.85 to 2 decimal places. And then pH equals 14 minus pOH, which is 1.85, and that gives us 12.15. All of these are 2 decimal places. So I'll just kind of write that across the bottom there. And our pH is 12.15. This was a weak base. So again, we have a pH greater than 7, and so it seems to make sense. In our last example, we are asked to calculate the pH and percent ionization for a weak base. This time we're not given Kb, we're given pKb. Be really careful when you're given pKb. I've seen this happen where the pKb will just be dropped into the mass action expression. We have to actually calculate Kb. The calculation is Kb equals 10 to the minus pKb. This calculation is shown in detail in another video. So for right now, I'm just showing the final relationship. So our Kb will be 10 to the negative 9.04. For sig figs, when we take the antilog, we go from number of decimal places, which is 2 decimal places, to 2 sig figs. So doing the math, negative 9.04, taking the antilog, we get 9.1 times 10 to the negative 10 for our Kb. Setting up our equilibrium, we have water plus A minus goes to HA plus OH minus. This is a mice table, so our units are molarity. We're not doing anything with the water. Our weak base initial concentration is 0.0152, and then we have 0 and 0, minus x plus x plus x, 0.0152 minus x for our equilibrium value, and then x and x. For our mass action, we have Kb equals HA times OH minus divided by A minus. Plugging in our values, Kb 9.1 times 10 to the negative 10 equals x times x, or x squared, divided by 0.0152. So we ignored the change in x, and we're going to check it when we're done. So continuing to solve the problem, we have 9.1 times 10 to the negative 10 times 0.0152 equals x squared, square root of both sides to give us x. Our sig figs are 2 and 3, so that will give us 2 for our calculated result. We have 9.1 times 10 to the negative 10 times 0.0152, and taking the square root of that to 2 sig figs gives us 3.7 times 10 to the negative 6. And this is hydroxide. So we'll check our assumption. 3.7 times 10 to the negative 6 divided by 0.0152 times 100. gives us 0.024. And that is okay. This value is also equal to our percent ionization. So this base is only 0.024% ionized. Finishing up our calculation, we have POH equals negative log of the OH, and that is 3.7 times 10 to the negative 6. Our 2 sig figs becomes 2 decimal places. Doing the math, we get 5.43. And our pH will be 14.00 minus 5.43. Everything, including our final result, is 2 decimal places, and we get 8.57 for our pH.